Hi all, welcome to the last video of CSM 70 final review session. I am Brian, and I'll be walking you through this final part, this final saga of the final review session for CSM 70. And in this final saga, we are going to be covering continuous distributions. Before we get into continuous distributions, let's talk about the difference between continuous and discrete distributions. So the way we define the distribution is firstly different. Continuous has a density function compared to a discrete where you have a mass function. The second thing that's very different is that we have an expectation for the way we calculate expectation is a little different too, because the way you define a distribution is different. And finally, our variance does stay the same. So for the expectation, I'm just going to write it down for you. The case of continuous, we have that integral of x times fx of dx. The other hand, you had this x times p of x, where p of x is represents the PMF. For this one, I'm also just going to point out this factor that people tend to forget, is that the variance comes from this equation, and you calculate this and you can expand this to get to these variance equations. Okay, let's go right into distributions that you have to know. Now, it's very hard to give intuitions for continuous distributions because we don't think about things from a continuous point of view most of the times. You think more on the discrete level, coin flipping. Continuous is not where we usually stand. But I am going to try and motivate it with some questions that you probably want to ask. For uniform, you want to ask the question of how can we get an interval of these values to show up? So for uniform, you have two values, a and b, and the value and x is going to fall somewhere in between a and b. For normal you've probably seen this. It looks like that. It looks like a usual distribution on an exam, for example. Sometimes some exams have two peaks, but it tends to be one strong peak of normal, and we can actually justify this by using the central limit theorem, which comes out later. Not in this final review session, but it definitely comes up. Central limit theorem says if you have a lot of samples, you can approximate it with a normal. So it has infinite support. You don't have to know that. It's symmetric about the mean, so it's completely symmetric on both sides, and you have random samples for any population. And the question you should be asking is what proportion of my data is far away from the mean. Geometric, the continuous exponential, and you can think of it as like the analog of a continuous analog of geometric distribution. Again, the question you'll be asking is how long do I wait until the first success? So let's just write something down. This is how it looks like. This is the f of x. This is the expectation. This variance looks very similar to geometric. For Gaussian, I'm going to write the f of x down a little more in the form that you've probably seen. A little more. 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared, right? Or for those of you who like to make things look good, this is the form you've probably seen it in. Okay, so that's f of x for Gaussian, and Gaussian takes in two inputs, mu and sigma. Actually, not just sigma, it usually takes in sigma squared. and then the expectation is mu, variance is sigma squared. And they're just given to you. Now, I've left out the uniform distribution. It's a little missing, so let's put it right next to here. Uniform distribution. The way we write it, we usually say x is uniformly distributed with a and b. And f of x, again, is uniformly distributed, so we get 1 over b minus a. 0 otherwise, if x is in a and b, and 0 otherwise. And the expectation of x, again, you uniformly sample it between a and b, so you expect it to be in the midpoint. And the variance of x, you can calculate this, and it's very interesting. It's very exciting. B minus a squared over 12. Again, this is something you can definitely calculate. Okay, for this question section, I'm going to be skipping the second part where you try to find the CDFs, and instead I'll focus my attention on darts, the dart game, and dying light bulbs. The reason being, I don't think the second part is as interesting. It's a little more mechanical. Okay, dying light bulbs. Suppose I have n light bulbs, x1 to xn, and they're distributed exponentially with lambda, and that's the lifetime of the light bulbs. And they're distributed IID. Okay, question A. Let's Z is equal to minimum of x1 to xn. So essentially it's the first light bulb that dies out. Find the distribution of Z. What is part B? What is the probability that x1 is the first light bulb to die out? So among x1 to xn, what's the probability that x1 is the first one? C, let y is equal to maximum, so the longest living light bulb, and let C be the shortest living light bulb. Find the CDF of the random variable y minus c given z. So you're given z, you're given what the minimum is, now you just want to find y minus c. Don't try to do calculation directly, use memoryless property. You can calculate it directly, but it gets very, very messy. Okay, part A. So here's what I'm going to do for this section. I'm going to just, their solutions are already written, and I think they're pre-written pretty nicely. So I'll be walking you through the intuition for why we do things. So in this first section, we have, let C is equal to minimum x1 to xn, find distribution Z. So for this part, here's what we do. We say, okay, we have, I have no idea how to draw a light bulb. And I have a feeling I'm going to draw it in a very weird way that probably doesn't represent what I want it to look like. Okay, like, let's say you have a couple light bulbs that look like that. I don't think this is how light bulbs look like. You probably want something like, it looks more like a mic, but assume that they're light bulbs. So this is the first one, x1, x2, lead to xn. Now, what we want to do when we find the minimum, remember that we are going to be trying to find this probability. If you want to find the distribution, all you have to do is define the CDF. You don't have to find a PDF. In fact, finding a PDF is usually very difficult. So you look for the CDF of Z, which is exactly this. Probability Z is less than Z. Now, it's very easy to calculate the complement because if C is greater than constant, then every one of them has to be greater than that. It's a little more difficult to calculate this because you don't know exactly where they are. So what we say is, okay, we're going to find this, and then we are just going to do 1 minus of. And to find that, we know that if C is greater than Z, then it means that every value is greater than Z. So we have that right there, which is exactly equal to, this is where the latex didn't really work out. we have lambda z times all the way until lambda z, and we have n of them, so we have nz. Okay, perfect. And then finally what we do is we just subtract it, 1 minus e to minus lambda nz. So what are some really smart things that has gone over here is, first thing, noticing that you can just find the CDF. The second part is, okay, the CDF is hard to calculate still, so let's find the complement, which becomes a lot easier. And finding complement is usually a trick that you use when you have something like the minimum. So two smart things that went in: find the CDF first and then find the complement, which is a lot easier to calculate. Okay. Part B. What is the probability x1 is the first light bulb to die out? I'm going to go with solution 1. You can use solution 2, but solution 2 is a little more messy, so let's go with solution 1. Every xi's are IID, so each one of them are equally likely to die out quickly. You know, if I have these light bulbs, each one of them are equally likely to die out quickly, so probably that this one dies out the first, 1 over n, because they're all identically distributed. So I'll go with that explanation. It's a very intuitive explanation that works because we know these are IID. Part C. Part C is a little more difficult. So notice that y is the time when all the light bulbs die out. And what this means is I know when my first light bulb dies out. I know z. And I want to find the time it takes, find how long it takes for n-1 to die out. Now, the way to do this is to use the memory list property, as the hint suggests. And by the memory list property, when the first one dies, the distribution gets reset. It gets reset, meaning, you know, whether the first one died, when the first one died, doesn't matter anymore. So essentially what happens is this turns into how long does it take for n-1 to die. And you can find the distribution, the CDF, by just calculating it. And again, lesson W, we did this calculation before. This is again going to be the probability. 1 exponential. I'm going to call 1 exponential, say, xi less than or equal to w to the power of n-1. We've done this calculation before in part A. Done this before in part A, where we actually made this just a complement. 1 minus probability xi is greater than or equal to w to the n-1 is equal to 1 minus e to the minus lambda w over n-1. Perfect. And that's it. So x of I greater than or equal to w, and we just plug it in, and we get 1 minus e to the minus lambda w to the power n-1. I'm going to skip over the second question because I think it's a little less interesting. So let's move on to dart game. Just for your interest, this dart game is actually the kinds of questions we tend to ask in our CSM 70 interviews for the new mentors. And it's a very interesting question. It's a very interesting question. Okay, as the question says, a player is equally likely to be good or bad. Okay, so, it's equally likely to be good or bad. It seems like we're going to be using some kind of Bayes rule here. So, Bayes rule. If she is good, she shoots the dart uniformly in a circle with radius 1/2. If she is bad, she shoots it uniformly in a circle with radius 1. The first dart is at a distance 1/3 from the center. What is the expected distance of the second dart to the center? So, okay, to solve this question, I think the key idea here, there's more key ideas down at the bottom, but my line of thinking when I see this is, okay, I want the expectation of the distance, right? Now, if I want to calculate the distance expectation, then I find the expectation distance given that she is good, multiplied by the probability she is good, plus expectation of distance given she is bad, multiplied by the probability she's bad. Okay, so I think that's a key idea, and we just have to fill in the blanks. Some more key ideas. This is a continuous probability. There are infinitely many places our dart could land, so don't think about this as discrete probability problem. Remember, then the problem will become discrete. It's not integers. It's just all the real numbers. More key ideas. So you can actually make a probability non-zero, taking a range from I plus I to I plus epsilon. So whenever you try to define any probability, right, like that the probability that X is going to land at this specific spot is always going to be 0. But you can make this, you can have a small trick to make this into a non-zero probability by saying that you want to find this probability instead, which is going to be non-zero because you're taking a range and you find the area under it, where epsilon actually epsilon should go to 0. It's very, very small, but it's not exactly 0. Okay, again, for this question, I'm going to go over this question in the way I've done it before, because I think the solutions are pretty well written, but I'll just be aligning some concepts. Okay, so the first thing is condition it on 1/3 to 1/3 plus epsilon. Again, why? Make probability non-zero, and then use Bayes rule. The Bayes rule, I'm going to copy my statement here. The Bayes rule is going to be exactly this. Okay, that's our Bayes rule. If a player is bad, the expected distance is 0 to 1. It goes from 0 to 1 since the player is bad. Y times f of y dy. And how do we get that? We get it by finding the CDF first. The CDF, remember, is going to be y squared. Because this is a circle, our CDF is going to be f of y is equal to y squared. Just remembering that this is equal to probability that y is less than or equal to y. The radius is less than or equal to y, so this is going to be y squared. And then to find f of y, you just derive it and you get 2y. Perfect. Okay. So that's 2y, and then you integrate over it and you get 2/3. If a player is good, the expected distance is half as large because the player shoots it uniformly with a radius 1/2. So it's half as large as 1/3. Again, you can do the same calculation if you'd like, going from 0 to 0.5. Y times 2y of dy. You can do the same calculations if you wish. Now let P be the probability that, I'm going to make this smaller. If you wish, you can use that calculation. Let P be the probability she is good given A. And what is A again? A is the condition that the distance was 1/3 to 1/3 plus epsilon. So by base, this is what we have. 1/2 times probability A given G, where 1/2 comes because probability A is equal to probability B is equal to 1/2. Sorry, not probability A. The probability that the player is good is equal to probability player is bad is equal to 1/2. There's a prior, and a posterior is going to be this entire expression, and we just have to fill in the gaps. And then we look for, so we need to find this and this, A given G and A given B. And how do you find that? Well, we just use this PDF that we have, use this distance, 1/3, comma 1/3 plus epsilon. We use that distance, and we just integrate over it. So yeah, again, A is distance was 1/3, comma 1/3 plus epsilon. All right. I won't show the calculation for that because you just have to integrate over 1/3, comma 1/3 plus epsilon for this particular question, where you do something like this: 1/3, 1/3 plus epsilon. I'm just going to show you one example for the PDF that you have. And you just multiply the PDF, and that should get you to the right answer. And then you just plug in the values, and then after that, you notice that this is going to be 4/5. Another way to think about this, if the epsilon is throwing you off, is to ignore the epsilon and just go from 0. It's just to think about it going from 0 all the way to 1/3. So if you go from, so if you have a circle and you go to 1/3, you can find the probability you go to 1/3 given you are uniform in 1/2 and you're uniform in 1. You can find them out, and hopefully that's a little more enlightening. Yeah, I should do that just for you because you're special. So this is 1/3. Let's say this is 1/2. The proportions are a little off, but let's ignore that. So if it's 1/2, we are saying, okay, what's the ratio of this circle compared to this entire circle, to this big circle? The ratio then is going to be, well, this circle, the area of that circle is pi over 1/9, and this is pi over 1/4, right? So in the end, I get something along the lines of 9/4. And then we do the same for the other one, where we have 1/9, pi over 1. There we have 1/9. Okay, so we have 4/9 and 1/9. So 4/9 and 1/9, we divide each other, and then we will get 4/5 and 1/5 as we want. So P is equal to 4/5. Because another way to think about this is, here we have 4 pieces, here we have 1 piece, and our sample size essentially decreases to 5. Okay, and therefore you just plug them in back into this part. So distance is good was 1/3, and we know that there's 4/5 opportunity of that, and likewise for the player's bad. In that case, it's 2/3, that's the expected distance, and we have 1/5. and you add them up and you should get 2 over 5. Just some final notes. Visualize things with pictures, so like I did with this one. Visualize it with pictures. Break down problems into shorter steps. Before jumping into calculations, just see if there's an easier way to solve these questions. So a lot of the times we use a lot of tricks that we can use, and you can solve these questions without using tricks, but that's going to require a lot of calculations. So make your life easy. And yeah, I hope you've enjoyed this video. I hope there was a lot of intuition to get out of these questions. So I urge you to go ahead, make your own saga, and open up a new chapter to this final review session. And I wish you the best of luck in your finals. So thank you, and I won't see you in the next video, but hopefully I'll see you around.